Good morning, class. The session is being recorded. We are looking at Chapter 5, Integrals, Sections 5.1 to 5.3, the Fundamental Theorem of Calculus. As always, formulas. Integration formulas, also known as anti-differentiation formulas. You need to be very comfortable to move on. The fundamental theorem of calculus, the method of exhaustion. In the old days, when they didn't have the formula for the area or circumference of a circle, how did they come up with the answer? This is the method known as the method of exhaustion. They started with a polygon with 3 sides and then 4 and then 5. They kept on adding as the number of sides get larger and larger. As you can see, the area as well as the circumference become closer and closer to the area and circumference of a circle. This method is called the method of exhaustion. The area problem can be solved in the same manner. So we are interested in finding the area under the curve between the function y equals f of x and the x-axis in the interval of a to b. If it's a geometric shape, we have a formula for, we can calculate the area. But when it's not, how do we achieve that? That's the idea behind the method of exhaustion. The method of exhaustion says we cut the area as follows into many subintervals. So for example, if I cut this interval of a to b to 4 pieces, such that the width we will call delta x, and it's fixed at b minus a over n. In this case, n is 4 class, okay? We cut it into 4, however many. As you can see, it creates 4 subintervals. And they don't look like a rectangle, but can be approximated by area of a rectangle. So how do you calculate the area? Well, this is the width, and we said it's fixed at b minus a over n. And what is the height? Well, if I choose this one to be the height, that means f of a. If I choose this one to be the height, that means f of this point, which is a plus delta x in general. And then the next one is a plus 2 delta x and so forth. So if I choose anywhere in between, it will work. For example, if I choose the left end point, I get this area for this one. Now, to be consistent, I'm going to go with the left end point for the next one. For the next one. And for the last one. As you can see, we can now calculate the area for each rectangle because we have the width, we have the height. On the other hand, if we choose to go with the right end points, so the height, for example, for the first one would be this much. So this would be the right end points. This would be the right end points on the rectangular piece. As you can see, the red versus blue, they don't have the same area. They both approximate this. And the method of exhaustion says, what if we add to the number of subintervals? As we add to n delta x becomes smaller, the approximation gets better. So to illustrate this fact, again, let's first write the area. The area under a curve, it is estimated by this. So summation of f of x by delta x as I goes from 1 to n is f of x of 1 times delta x plus f of x of 2 times delta x plus the last one, where delta x is b minus a over n. So the function is a positive function in some interval of a to b. We want to find the area between the function and the x-axis. So let's look at the simple example where f of x is x squared plus 1. I hope everybody remembers y equals x squared and shoot it up by 1. Here's the graph. By the way, this is a portion of a graph as we go from 0 to 2 that really goes this way. Let me just draw this in essence. Here's the rest of it, class, okay? This is the graph. However, we are shading only from 0 to 2. So let's stick with that. Now, how many subintervals are we going to go with? Normally they tell us, but let's start with 4 just for the sake of argument. When n is a 4, delta x is b minus a over n, which is 2 minus 0 over 4, and it makes it 1/2 or 0.5. So we're going to cut this into 4 pieces. So 4 subintervals, as you can see. What is the width? The width is fixed at 0.5. Delta x equals b minus a over n. More specifically, 2 minus 0 over 4, which is 1/2 or 0.5. What is the height? You can go with the left endpoints, with the right endpoints, with midpoints, with any point in between. It makes no difference. It's important that if you pick any point, just for the sake of argument, if you pick this point, you can say this is the height f of this point and draw this rectangle, just as an example. Of course, to make life easy, we are going to go with the left and right endpoints. One way that can make this process easy, if you draw the following line segment. This is A, which happened to be 0. This is B, which happened to be 2. We are going to cut this into 4 pieces. Therefore, we have 0.5, 1, 1.5. So now we are going to go with the right endpoints. That means obviously we are looking at the height at those points. This graph clearly shows that. So those are the points. And to calculate the area is the width, which is fixed at 0.5 times the height. So this one has a height of f of 0.5. The next one has a height of f of 1. The next one half of 1, f of 1.5. And the last one, the height of f of 2. So if you're looking at this line segment, for the right end points, ignore the first one. So you want f of 0.5, f of all of these points except f of 0. So you want to add them up and times delta x as follows. R sub 4, the reason we call it R because it's the right endpoints. And we are really using this formula, class. We are using this formula Delta x times f of 1/2. See, we ignore the first point. Why are we ignoring the first point? Because of the right endpoints. F of 1/2, the next one f of 1, and all the way to the last. You can factor out the 1/2 and just write 1/2 times f of 1/2 plus f of 1 all the way to the end. You do the math. Now, what is f of 1/2 as an example is 5/4. Why? Just plug in 1/2. It gives you 1/4 plus 1, which is 5/4. F of 1, plug in 1 squared, 1 and 1 is 2, and so on and so forth. Add them up, and the answer is 5.75. 5.75. We are going to repeat the same thing, this time with the left endpoints. Take a look. We are using this point, this one, this one, this one. We don't use the last one. In other words, if I go to the line segment, I'm going to use all of these points except the last one, or B. So one more time. For the right endpoints, we don't use the A. For the left endpoints, we do not use the B. The width is fixed at the same number, delta x equals b minus a over n, which is 0.5 or 1/2. And for the height, we use the functional value at all of these points except 2. For example, f of 0, if I plug it into the function, I get 1. And 1/2 gives me 5/4, so on and so forth. Notice this portion is the same as this portion, so it will really cut down in the number of calculations you have to do. So put them all together. You find the area for the left endpoints to be 3.75. What does it mean? As you can clearly see, over here, with the left endpoints, the area of the rectangles underestimate the actual area. In this case, for the right endpoints, they overestimate because of the nature of the graph, which is an increasing. Therefore, the area is between the two numbers. We may not have the actual area, but we have some idea as to the interval for the area. Let's repeat the same thing. But this time, instead of n equals 4, let's just change it and use a larger number. Why don't we go with number 8? We are looking at the same situation, the same graph, but this time we want to use a larger n to illustrate the fact that the approximation gets better. So if we use 8, then delta x is b minus a, 2 minus 0, which is the same 2 over n, 2 over 8, 1/4 or 0.25. And again, line segments, really, if you have this line segment of A to B, and you're going to cut that into 4, now 8 equal pieces. This may not be to scale. So you have this one as 0.25 or 1/4, 0.5 or 1/2, 0.7 or 3/4, 1, 1.25, 1.5, 1.75. And we are going to use the right endpoints first. Again, it's going to overestimate. Clearly, we can see that. So delta x times f of x of I, we're going to add them up. So the very first point is 0.25 or 1/4, f of 1/4. So if you look at your line segment, you use all of them except A, remember that. So 1/4 or 0.25 all the way to 2 or B. Do you see that? All of it. Now, what is f of 1/4? Let's go to the original function. 1/4 squared is 1/16 plus 1, 17/16. And you calculate the next and the next. By the way, on purpose, I left it as 2/4. So we can see 1/4, 2/4, all the way to the last one, which is 8/4. Needless to say, 2/4 is 1/2. So you do the math, and you end up with the following answer. We do exactly the same thing for the left endpoints. And remember, with the left endpoints, delta x again, or the width is fixed at 1/4 or 0.25, but is the height. F of 0, all of these points are used except B. So f of 0, f of 0.25, all the way to f of 1.75 or 7/4. Again, I want to show you this. This portion is the same as this portion, which means it's going to cut down on the number of calculations you need to do. It's really helpful. You calculate and you come up with the following answer. Again, what is the area? We don't know, but it's between the two. Remember what happened. In the previous case, we found the numbers as follows. 3.75. This was when n was 4. This is when n is 8. And clearly, we have a better approximation here because the two numbers are closer to each other. Now, obviously, if you add to n, the numbers get even closer and closer. And as far as approximation is concerned, you continue until the two numbers differ by only, I don't know, 0.1, 0.01, or whatever the question will ask you. So clearly, if you add a few more, they become extremely close, which means this is an approximation, and this approximation gets better as n gets larger. We demonstrated with this example that approximation gets better as n gets larger. So here's the Riemann sum and the fundamental theorem of calculus. Suppose a continuous function f is defined on the interval of a to b, closed interval of a to b, if the interval is divided into n subintervals so that delta x is b minus a over n, and a sub 0 is a sub 1 is a plus delta x, all the way to the last one, a sub n is a plus n delta x, which is equal to b, n times delta x. This summation is called the Riemann sum. And this summation is an approximation of the area under the curve. But the exact, take a look at this one. The exact is when we use the same thing, but we add this piece, taking the limit as n goes to infinity. This is the area under the curve exactly. Now, we have something called fundamental theorem of calculus, or FTC for short. This reads the integral of a to b f of x dx is capital F of b minus f of a. First and foremost, this is identical to this. This is by definition. These two are identical by definition, class. If f is a positive function, therefore this becomes the area under the curve. What is capital F of B minus F of A? This is FTC. This takes a long time to calculate. This is very easy to calculate, where capital F prime is lowercase f. So here's the fundamental theorem of calculus. ddx of the integral of a to x f of t dt equals f of x, given capital F prime equals lowercase f of x. The integral of a to b f of x dx is capital F of b minus f of a. We're going to elaborate on all of this shortly, but here's the synopsis of that. This one was discussed. If f is a positive function, this is the area under the curve, and it's precisely equal to that, and it's easier to calculate at this one. So you find the antiderivative, any antiderivative, and you evaluate it at the top limit, you evaluate it at the bottom limit, the difference, the answer. What about this one? The derivative of the integral is the function itself. We want to discuss this concept with more details. So let's see, what is this representing? Let's make sure we understand this one. Integration symbol. This is an elongated S. Looks like an S. It's an elongated S representing a sum. Lower limit of integration. Upper limit of our integration. Integrand, the function we are integrating. Now this is a dummy variable. What does it mean? It's called a dummy variable because the answer doesn't depend on the variable chosen. The dx simply indicates that the independent variable is x. And this whole thing is called a definite integral because it gives you a number. If we don't have the lower and upper limits, it becomes capital F of x plus a constant, which is an indefinite integral, a family of functions. This is a number. Without a and b is a family of functions. So let's look at this one. The integral of a to b f of x dx is a number. It doesn't depend on x. We could use any letter in place of x without changing the value of the integral. So if I said the integral of a to b f of t dt or the integral of a to b f of x dx makes no difference. Its approximation is the summation, which is called the Riemann sum. Remember that? There's an approximation of this. What is the exact? When we take a limit and we let n go to infinity. This is a Riemann sum. This is the limit of a Riemann sum, which is exactly equal to the integral of a to b f of x dx. So this is one of the FTCs. And just to, again, remind you, the second one that we showed in the previous page, okay, the dx of f of t dt as we go from a to x is lower f of x. I want to discuss this one also. This simply put means integrate this from a to x. This function integrated from a to x. Remember, a is a number, x is a function. So it ultimately becomes capital F of x minus capital F of a. When you differentiate that, it gives you lowercase f of x. This gives you capital F of x minus capital F of a. You are going to differentiate this And I hope you realize it gives you, if you differentiate, gives you capital F prime of X minus F of A is a number, 0. What is capital F prime of X? Lowercase f of X. What does it mean? Integration and differentiation, they undo each other. They are reverse process. Okay, let's evaluate the following integral using areas. Notice I put a dot in between on purpose because if I wrote dx, you may not notice it's 1 times dx. It's obviously the same as saying the integral of a to b dx. However, by putting 1 times, we are showing the reader this is f of x. So y or f of x equals 1 is a horizontal line, and we're going to draw that over the course of a to b. Now, what is a, what is b? Could be any number. It doesn't matter. You can make both of them positive, both of them negative, one of them positive, one of them negative. It doesn't matter. Somewhere from a to b, clearly b is on the right of a according to the given interval. This represents the area under the curve of this rectangular shape as we go from a to b. So what is the width? This much, b minus a. What is the height? This much, simply 1, and it's fixed at 1. So b minus a times 1 is the answer, and we can easily see the answer. Now, why are we using it by the method of areas? Because we want to show that this works for basic cases where geometry is known and we have a formula for it. It also works if the geometry fails. That's what we are moving towards. So what I want to show you, the answer using FTC. So this is your function, and I hope you realize the antiderivative is x. We are going to evaluate it from a to b. You first put in the upper limit minus, you put the lower limit into the function. And as you can see, they are identical. So what is the difference? Normally, FTC gives you a faster answer. Both of them give you the same answer. And that's the idea behind this question. To make some more sense out of this, let's look at this one. We want to use the same concept, the signed area interpretation of the definite integral to compute this. So first and foremost, what is our function? We have to realize that y or f of x is x, and the interval of interest is from -1 to 2. So we are going to graph the line y equals x. I hope you remember the line y equals x goes through the origin. And to go from -1 to 2, that means from -1 to 2, let's draw it to 2, -1. Why am I using 2 different colors? Because when you have a function which is positive, this represents the area under the curve. But as you can see, a portion of it is positive above the x-axis, a portion of it negative below the x-axis. So it represents the difference of areas. It's the net area. So the area of the green minus the area of the red. That's what we need to find. And I hope you realize that area for any triangle is A equals 1/2 base times the height. Let me put this point at 2, 2 in this triangular shape. Each leg is 2, and the area becomes 1/2, 2 times 2, which is 2. In the case of a red one, this is located at -1, -1. So this distance is 1. We are looking at the distance, okay? 1/2 times 1 times 1, which is 1/2. So the area for the green, we found it to be 2. For the red to be 1/2, we have to subtract the area of the red from the area of the green, and that results in 3/2. What I want to quickly show you is that we could use FTC. So the function is x, everybody. The antiderivative is 1/2 x squared. And the reason I don't need the constant, class, because the constant will go away. You have to plug in 2 and -1, subtract 1 from the other, the constant goes away. So if I put the 2, I get 2 squared minus -1, quantity squared. So 4 minus 1, or 3 times 1/2, 3/2, which is the same thing. Again, why are we using both methods? We want to make sure everybody understands the area using, in this case, geometry works. The area using FTC works. So what if the geometry fails? It's not a shape we have a formula for. Here's what I'd like you to do. I want you to graph the function, figure out the function. What is your y or f of x? Graph it from A to B, and then come up with the answer. I'm giving you the answer. Make sure you can justify this. I highly recommend you do it both ways. We want to evaluate the integral of 0 to 1 x to the power of 7 dx. So what is the antiderivative for x to the power of 7? Is x to the power of 8 over 8. We don't need the constant. From 0 to 1, we plug in 1 first. We get 1 over 8 times 1. Then we plug in 0 minus 0, so we get 1 over 8. And here's the tip that we discussed, and pay attention to that. Even if we use a constant, it will go away because we drop him here. Okay, class? Even if you put a constant, you don't need a constant. This is a definite integral. This is a number. Does this represent the area under the curve? If the function is positive, yes. Otherwise, it's the net area, difference of area. So we don't want to mix up the two. Here's the next one. Clearly, everybody knows x to the power of -1 is the same as 1 over x. Therefore, the answer is ln x. And an absolute value gives us ln 2, ln of the upper limit, minus ln 1, ln of the bottom limit. We know ln 1 is 0, and ln 2 is the perfect answer, is not an approximation, exact answer. Pay attention to the fact that we use the absolute value. If you take a look at this question, we are pretty much repeating the same thing with different limits. So let's just write the same answer, ln x in an absolute value with different limits. Now, in the first case, if you didn't use the absolute value, it wouldn't make any difference because both limits 1 and 2 were positive. Now, it makes a huge difference, and you would be wrong if you don't write it. So we end up with ln of absolute value of -1 minus ln of absolute value of -2. If you don't have an absolute value, logs, or in this case, natural logs, are not defined for negative numbers. So the answer is undefined. That's why you must use the absolute value. So ln1 minus ln2, and I hope by now everybody knows ln1 is 0. So negative ln2 is your final answer. We want to evaluate the integral of 0 to pi sine x dx. The derivative of sine is cosine, but the integral of sine is negative cosine. So we are going to plug in pi as the upper limit. So minus cosine pi minus, then we plug in the lower limit 0. What I'd like you to remember is that this one is negative 1. Cosine of pi is negative 1. Cosine of 0 is positive 1. So what you have, minus minus 1, which is positive 1, minus minus 1, which is positive 1. 1 and 1, they add up to 2 as the final answer.